Okay, so we brought up that concept of a reference angle. That reference angle does come off of our unit circle. I'm going to make that a little bit more horizontal than that. And what is, remember, this is our reference axis or reference diameter here. If we have an angle, the reference angle is the nearest angle to that diameter. So we might have, 40 degrees here as an angle. Well, in the first quadrant, the angle is the reference angle. So 40 degrees is the reference angle. But if I have an angle over here that's 110 degrees, 110 degrees would be right there. The reference angle is the closest angle to that reference diameter. Well, since this horizontal is the reference diameter, that's the closest angle to it, which is going to be how much? 70, good. Because we have to get up to 180 degrees here. What if I have an angle that's right here at 320 degrees? The 320 wraps around here, but the reference angle has to go to that horizontal. The closest to the horizontal is right there. What would that angle be? 40. And of course, we might have like 250 degrees. Its reference angle is going to be right here, which is going to be how much? 70. So the question is, why is that reference angle important? Well, we're going to throw out some angles here, and we're going to look at the reference angles. I'm going to start with 60 degrees. What is the reference angle for 60 degrees? 60. Somebody on your calculator find the sine of 60 degrees for me. 0.866 is correct. Well, let's take a look at another angle over here. This angle is 120 degrees. What is its reference angle going to be? 60 degrees. Somebody type in the sine of 120 for me. Yeah, sine of 120 degrees also equals 0.866. If I go down here to 240 degrees, what's its reference angle? 60. Now, without typing it in, does anybody want to guess what the sine of 240 degrees is going to be? Close. Go ahead and type it in. There it is. Negative 0.866. Because that's down below the horizontal. There's one more angle over here that has a 60-degree reference angle. Can you figure out what it is? Careful. 300 degrees. There we go. Its sine would be negative 0.866. So you can see all of those angles that have the same reference angle, their signs are either the same or they're negatives. They all have a sine of 0.866, just two of them are positive, two of them are negative. What would the cosine be here for this one? Well, cosine of 60 is 0.5. Well, guess what? Cosine of 300 is also 0.5. A little easier to see that one because it's the same spot on the graph. It's on the axis. Cosine of 120 negative 0.5. Same distance, just in the opposite direction. Cosine of 240 also negative 0.5. So the sines and cosines of those angles are related if they have the same reference angle. Why is this important? Well, with your new calculators, for the most part, it's not horribly important. Once upon a time, the very first calculators we had only did trig functions from 0 to 90 degrees. So you had to convert, if you wanted to find the sine, you wanted to find the sine of 162 degrees, you had to find the reference angle. That reference angle was 18 degrees. So you found the sine of 18 degrees. Even before those first calculators that didn't do anything above 90 degrees, we didn't have calculators. Well, you had to use trig reference tables. Those reference tables, you didn't want to list out angles from 0 to 360. Actually, it keeps going beyond that, by the way. There's more angles here that would have a reference angle of 60. I could go past 360 and go to 420 degrees, couldn't I? That would end at the same spot, have the same terminal sine as the 60. It keeps going. So you really don't want to have reference tables for your trig functions from 0 to infinity. So they just went from 0 to 90, and then they used the reference angles to use those trig functions for other things. The one that's really important to us as far as reference angles is the sine. The sine is very important because the sine of 162 is equivalent to the sine of 18 because they have the same reference angle. Here's the 18 degrees, there's its sine. 162, there's its sine. How about the sine of 97 degrees? That's going to be equivalent to the sine of what? Yeah, 97 would be there, 83 would be there. 97, 90. What's the relationship we see between these angles here, between the 162 and the 18 and the 97 and 83? They are supplements. Very good. Supplementary angles have the same sign. So as we get going here and we start to solve triangles, if we have a picture of the triangle, it's no big deal. But if we're told that we have a triangle and the sine of an angle, let's say the sine of angle B in that triangle is 0.5. Well, if you do the inverse sine of 0.5, it gives you 30 degrees, right? Well, if we're working in right triangles, that's no big deal. 30 degrees is our answer. But at some point, we're going to talk about something called oblique triangles, where they don't necessarily have to be a right triangle. And if we're looking at oblique triangles, there are two possibilities. Angle A could be 30 degrees, or angle A could be 150 degrees. So whenever you do an inverse sine, like I said, inverse sine is the important one. Whenever you do an inverse sine, there are two possible angles it could be. Does that make sense? Okay, I'm gonna let you guys have some time to finish up that quiz. Okay, good question. What other information are you given in that problem, though? Okay. You know that on the unit circle, sine of 0.4 is this side right here, right? That means this side is 0.4. What other side of that triangle do you know? You know the hypotenuse is 1, right? So this here is the cosine of that angle. If I just label that as A, B, and C like that, I know A squared plus B squared equals C squared, right? So A squared plus b is 0.4 squared equals 1 squared. You solve for a. Remember, a is the cosine of x. So once you find that value, that is the cosine of x. Anything else that you have questions on? Okay. Anybody else? Okay, so we had left off last class. We were taught yesterday. We're talking about right triangles. If we have a right triangle, doesn't matter what orientation it's in, we already know one piece of information, of course, and that's the right angle. If we know any two other pieces of information, as long as at least one of them is a side, we can find everything else. So if we know that this here is 18 inches, and let's say we know that this here is 64 degrees, we can find the rest of this triangle. So first, what's this angle here have to be? Oh, the exact number. 26, very good. The three angles have to add up to 180, but we can even take it shorter than that. Since we know that's 90, we know these two have to add up to 90, or have to be complements. Now from there, we can find any side I want to. I'm gonna find this side here first, the hypotenuse. I'm gonna use the angle we were given just in case we did something silly and messed up the 26 degrees. So we're gonna use the 64 degrees. So the x is the hypotenuse, the 18 is which side? The adjacent. What trig function is hypotenuse and adjacent? The cosine is adjacent over hypotenuse. So I write out that function and let's fill in what we know. Do we know the angle? Yes, I'm gonna fill in my 64 degrees. Do I know the adjacent side? That's the 18. The hypotenuse is what we're looking for. That's x. What do we do from there? Okay, well, what I would do is, since we're looking for a side, is I'd make it a proportion. Yes, we are going to do the cosine of 64. Of course, 1 times 18 is 18 divided by the cosine of 64. So it's 18 divided by cosine 64 degrees. Divided by, not times. .06 we get. So it's 41.06 inches. Now to find this side, we could do a squared plus b squared equals c squared, which is just fine if you wanted to use that. I'm going to treat this, it's the opposite side with my 64, and I'm going to go back to the information I was given. I'm going to try to avoid to use this to do any other calculations if I can, because I calculated it. And even if I did do it correctly, at the very least it's rounded off. And by reusing it, I'm compounding those round off errors. I mean, there are cases where I have to go back and use that measurement, and that's fine. But I'd rather try to avoid it if I can. So I have the opposite side and the adjacent that I'm given. What trig function is that? Tangent. So again, I'm going to plug in what I know. I know the angle is 64 degrees. The opposite side is what I'm looking for. The adjacent side is 18 inches. And so again, I will make this a proportion and cross multiply. So it's going to be tangent of 64 times 18 divided by 1. So 18 times tangent is 64. I don't have to divide by 1 because it's not going to do anything. 36.91. So this opposite side here is 36.91 inches. Now, if I wanted to, I can double check this to make sure 36.91 squared plus 41.06 squared equals the 18 squared. Oops, I did that backwards. 36.91 squared plus 18 squared equals the 41.06 squared. And it'll be within round, it won't be exact, it'll be within round off errors. Any questions there? So why is this important to you guys? Well, let's say you have a post that you need to reinforce. And you're gonna put in a guy wire. Let's say that's gonna connect up here 40 feet above the ground. And it's gonna come out here. That will come from here. Let's say the maximum distance you can get out there is 18 feet. I want to know what angle we're going to have on that. Well, here's my right angle right here, isn't it? What sides do I have? Opposite and adjacent. Of course, that means what trig function? Tangent. So let's fill in what we know. We don't know the angle. We know the opposite side is 40, the adjacent side is 8. Now here we are looking for the angle, so it's a little different. Before we were looking for missing sides, so we made it a proportion and we cross multiplied and divided. When we're looking for the angle, what do we have to do? Inverse tangent. So the inverse tangent and the tangent cancel out. Theta is, what's the inverse tangent of 5? Not 5. My 1 disappeared. Should be the inverse tangent of 40 over 18. Yeah, my 1 disappeared on me. It should be 18, not 8. 65.77. There we go. This should have been 18 here. The 1 disappeared somehow. I had said 18 on that, at least I hope. So that's going to sit at 65.77 degrees. Or the other side of it. Let's say you're going to anchor that post. You know that the spot that you're going to anchor to is 28 feet off the ground. You know that when you anchor it, your maximum angle here, the higher that angle is, the less effective that support is. The lower that angle is, in other words, the further we bring it out, the lower the angle will be, the more support that guide wire has. So let's say that our maximum angle there is 60 degrees. If it's more than 60 degrees, it's not going to hold. And let's say we know we need 3 feet on each end to make our connection. Because you have to be able to double the cable back over and clamp it to itself to connect it. So, how long of a piece of cable do we need to take with us? Or how long of a piece of cable do we need to cut? Well, we'll find this length right here using the triangle. There's our right angle. The 28 is what side? Opposite. We're looking for what side here? The hypotenuse. That is sine is opposite over hypotenuse. So we know the 60 degrees. Opposite side is 28. We are looking for that hypotenuse. Since we are looking for a side, I make this into a proportion and we'll cross multiply and divide. 1 times 28 is 28 divided by the sine of 60 is 32.33. So 32.33 gets us from here to here. What do we still need to do to it? Add 3 feet on each end, so add 6 feet. So we need a 38.33 foot piece of wire, so 38 foot 4 inches about. What do you think? Not so bad. Another application of these we covered a lot of crap in the last couple days. Sorry. Another application of these is when we're looking at AC current with inductors and capacitors. You look at phase. And if you look at the total impedance or the voltage across different components of that circuit, so let's say we've got a circuit with a capacitor in it. When I first open, open or close the circuit, I should say. So I start out with 0 volts on that capacitor, but let's say I have 50 volts here. When I first close that circuit, let current start to flow, all 50 volts is on that resistor, isn't it? The capacitor has 0 volts on it. Over time, though, what happens to that voltage? This voltage increases, and as the voltage on the capacitor builds, the amount of current flowing decreases, right? So as the current decreases, the voltage on the resistor goes down until the opposite occurs. If it's a sine wave, if it's a alternating current, of course, you've got positive voltage, negative voltage, positive voltage, negative voltage. So it pushes and pulls. But the voltage on the capacitor trails the voltage on the resistor. So it's called a phase diagram. From that circle, if we take the circle out and just use the axes, this is 0 degrees, this is 90 degrees. Well, the voltage on the resistor will peak at 0 degrees, or if we call it 0 degrees. That's the voltage on the resistor. The voltage on the capacitor peaks 90 degrees later. Does that make sense? So the total voltage in the circuit adds up, but what we're looking at is impedance. So if you look to combine the impedance of a circuit, that phase shift is important. So let's say we have a 2 kilo ohm resistor. And let's say we've got an impedance on that capacitor. You guys went through calculating equivalent impedances, right? For capacitors? A little bit? All right. Let's just say the equivalent impedance on that capacitor is 1 kilo ohm of impedance. So our total impedance is found. We've got 2 kilo ohms, 2,000 here, and 1,000 here. We find the resultant of those vectors. That's it right there. So basically what we end up with is a triangle. Here's the impedance, the 2,000 ohms from the resistor. Here's the impedance, the 1,000 ohms from the capacitor. Total impedance is this hypotenuse, which is the square root of 2,000 squared plus 1,000 squared. Which gives us 2,236 ohms is our total impedance. Our phase angle is in the inverse tangent because we have opposite and adjacent. I'm leaving off zeros here, obviously. So 26.57 degrees. But there are a lot of applications where trig comes into our electronics. We'll talk a little bit more about those phase angles later. For now, I believe the last page I gave you was that smaller packet, page 347, 348. I'm going to have you guys work on page 714, 715, exercise 35-1, 1 through 16. I believe that is back in your other packet. No, that's in your